So once again, we are meeting for another topic, and today we are going to cover something on wave shaping and pulse generating circuits. So wave shaping is basically the process of altering whatever I refer to as non-sinusoidal waveforms by using circuits or by passing them through circuits. So if you alter a waveform, then non-sinusoidal waveforms, we're talking about the wave shapes. And that one can only be done through a process of passing them through a circuit, which can comprise maybe a diode, a capacitor, and inductor as the process. But in this case, the purpose for mainly wave shaping is to change the duration or the period that is required for us to be able to turn the circuits or activate the circuits, or to get a resultant waveform that's able to be given in terms of the drawing or graphically to see the impact of the circuit. So we are saying that wave shaping is a process through which a non-sinusoidal waveform is passed through an electrical circuit that comprises of different components. Example of the component is the diode. Then in this case, we're going to understand why do we have to have the wave shaping circuits. So functions of wave shaping circuits. So number one is to generate a waveform that is different from the others. To generate a waveform that is different from the other. We'll go to number two. To limit the voltage level, limit the voltage level for preset circuits. Limit the voltage level for preset circuits or switching circuits that can only operate on specific conditions. And number three is to cut off positive and negative positions. To cut off positive and negative positions that are not needed, that are not necessary at the outputs. And lastly, whatever we talk of the wave shaping for number 4 is to hold a waveform of a particular, to hold a waveform of a particular shape. To hold a waveform of a particular shape or DC level of a particular DC level. So basically, these are the reasons why you have the wave shaping circuits. And so from here, we need to understand on the types of wave shaping circuits and how we can now relate them to the functions now. So because of having these different functions, we normally relate this with the whatever I can refer to as the nonlinear and linear circuits. So we're going to have the types of wave shaping circuits. Wave shaping circuits, types of wave shaping. So we normally talk of the linear wave shaping circuits. Number 1 is the linear wave shaping circuits. So when we talk about the linear wave shaping circuits, we are talking about circuits that basically use components like the inductor, capacitor to alter the waveform. So these are circuits that use linear elements. These are circuits that use linear elements, e.g. what I refer to as an inductor, a capacitor, maybe and resistors. So another class of wave shaping circuit is the nonlinear wave shaping circuits. So they basically use the non-linear elements in changing the amplitude. Of the waveform, changing the amplitude of the waveform. And the example of this is whatever we can refer to as a diode. So we're going to discuss the types of wave shaping circuits in details, and particularly for the cases that we're going to apply, and particularly we're going to get, and also we are going to get these types of application in terms of the practical life experience. So we're talking about the linear wave shaping circuits. So the first one we're talking about is the differentiating circuit. So we're going to discuss this with the aid of a diagram, so for us to be able to understand it very easy, and for us to have the figurative circuits that we expect if asked, we're able to understand how it works. So the first thing we're going to do is to draw the diagram that explains us this. So I'll draw the diagram here. When you look at this diagram, capacitor is connected in series with the input, and these are the terminals of the capacitor and how it's connected. So at the input, at the input, the capacitor is in series, but at the output, the resistor is shunted with the load. So whatever you need to understand is this is also referred to as a high pass filter, and the reason it's a high pass filter is because at high frequencies, the capacitor behaves like a short circuit conductor or just a wire, but at low frequency, the capacitor will block the low frequency signals. Because of that, then we talk of differentiating circuits. So when we are able to do that, we are supposed to understand of how these things operate. So when the frequencies are very low, the output recorded here is nearly zero. But the frequencies are very high, there's an output recorded, which is referred to as VO. So when you ask to this, and you'll basically know how it operates. So at low frequencies, the capacitor blocks all the low frequency values. At low frequencies, the capacitor blocks the low frequency signals. While at high frequencies, the capacitor short circuits and therefore an output voltage is recorded. This makes this circuit to be referred to as a high-pass filter. It may just be referred to as a high-pass filter because it only conducts the high frequencies to the output. So we're talking about why do we apply the differentiating circuits. Number one is to generate a step signal from a ramp signal. And number two, we are going to talk about generate a square waveform from a triangular waveform to generate a square waveform from a triangular waveform. And number three, we're going to talk about generate a series of narrow pulses to generate series of narrow pulses from rectangular or square waveforms. So we're going to discuss our second circuit about the linear wave shaping. In this case, we're going to discuss what I refer to as integrating circuits. So as is the norm, then we are going to start with the diagram so that we understand how the integration part of it is. So to integrate circuits, the first thing you need to understand is to draw the diagram. So in this case, it's just the reverse of the first circuit, given that now in this case now we're going to connect the resistance series with the input and the capacitor shunted with the load of the output, shunted at the output. So at low frequencies, then we are able to record an output across the capacitor, but at high frequencies, the output is grounded with the capacitor. And that one tells you about one of the functions that you now apply in capacitor form. That anytime you don't want the high frequency values to be measured at the output, we have to connect the capacitor as parallel to the load. So at low frequencies, then you shall have the value, the resistor conducting, and the capacitor is charged. Then at that point, we are able to record an output across the terminals of the capacitor. But at high frequencies, as much as the resistor will allow it to pass, but the capacitor will ground the high frequencies to the ground. So at the end of the day, we have no output. So at low frequencies, an output is recorded. At the output terminals, while at high frequencies, no output is recorded. Therefore, this type of circuit is also known as low-pass filter. So we're going to also look at the applications of the integrating circuits, or whatever referred to as the low-pass filter. So number one is to perform mathematical integration integration in analog computers. Application number two is to generate triangular waveform from a square waveform. To generate triangular waveform from a square waveform. And number 3 is to generate a sawtooth from a rectangular waveform. To generate a sawtooth waveform, a sawtooth, whatever it also referred to as a sawtooth, whatever referred to as the triangular waveform. Triangular waveform, sawtooth from a triangular from this is not purely, it's a bit of curved, from the square waveform. From the square waveform. So other times is that when we talk of the triangular, there's a pure triangular and there's a triangular with curved edges. So this one is a bit of with sharp ends as compared to this as normal triangular. That is with the sine waves or the normally happen. But this one is a relation with this one. The difference is because of the edges, but they appear to be like similar in the expression. And that's why the number 2. We are talking about a pure triangular, but this is a sawtooth. Sawtooth is a bit of zigzag, but the shapes are appearing as a triangle. Then we are going to go to the second type of the second types of the wave shaping circuits, the nonlinear wave shaping circuits. So also these things, we talked about using the nonlinear components, e.g. a diode. And one of the things we realized that we are able to use this basically for clipping. So in this case, we have to classify how many types are there. So for this, the first one I'll have, there are basically 2 types. They are basically two types. One is what I refer to as clipping. Circuits. So when talking about clipping circuits, what do we understand by the clipping circuit? The clipping circuits is basically removing part of the waveform. So these are circuits that are able to cut part of the output waveform so that it appears as expected, but a bit of it is chopped off. So this is basically, these are circuits that chop off or chops off part of the expected part of the output waveform, cuts out part of the output waveform. So it has got subunits. They include Roman 1 is positive clippers. Roman 2 negative clippers. Roman 3 whatever referred to as biased clippers. Biased clippers. So we're going to discuss this a bit in details. and also with the diagrams. So we're talking about positive clipper is we're talking about when they see the waveform of the output waveform, the positive part of the sine wave is chopped off. And negative clipper, the negative part of the sine wave is chopped off. But bias clipper is one that is able to have some control of clipping off the negative and the positive part of the sine wave using an applied voltage. So basically that we need to understand that. So we're going to talk about this type of clippers in details with also the output waveform, so that when you're describing the operation, you're also able to reflect at the input and the output waveform that is expected. So this is a positive clipper, and when you look at it, the diode is connected in series with the input. But in this case, this circuit operates like this. When there's an input, a sine wave input as indicated alongside the diagram, when this is more positive, the diode is reverse biased and there's no conduction. At that point, there's nothing we're recording at the output. That's why there's there's a space here for no wave shape. So, but when at the negative part of the sine wave, the diode is forward biased, and we're able to record an output. So at the end of the day, you understand that our circuit is able to give us, is able to clip the positive part of the sine wave. And that's why we talk about as the positive part of the sine wave. And it's not measured across the output. So whatever we're going to measure is the negative. That's referred to as positive. With the title, just as the title is a positive clipper, it removes the positive part of the sine wave. So from that simple explanation, I'm able to understand. And the circuit below here is also a positive clipper. But how does it work then? How does it remove the positive clipper then? In this circuit, during the positive part of the sine wave, the diode will conduct, and it will conduct to the ground. So no signal will be recorded at the output because the diode has shorted, is conducting to the ground. So in that case, we shall have clipped the positive. But during the negative side part of the sine wave, at this point in time, then the signal will conducted here, and the diode is going to be reverse biased. When the diode is reverse biased during the negative part of the sine wave, then the output will be recorded because the diode will not conduct. So the positive part signal is conducted to the ground, and so whatever we record is the negative. And that's how this one is in a similar scenario in operation with this one. This is just an alternative to your drawing, so that in the event that you want to draw a simpler diagram, you understand that once the resistor is in series, the diode is connected to the ground, and the positive part is ground, the negative of the part of the diode is grounded. And once it's in series, then the negative terminal is connected to the input. Basically, that's how this diagram works. So how does it operate? Operation. During the positive part of the sine wave, the diode is reverse biased, and so it acts as an open circuit. Therefore, no output is recorded. During the negative part of the sine wave, the diode is forward biased, and the voltage is conducted to the output. Hence, the positive part of the sine wave is clipped. So this is basically the simple operation that it has. So if you are going to use this for the purpose of explaining the same, then in this case, during the positive, the diode is conducting and there's no output recorded. But during the negative, the diode shall be reverse biased and there'll be an output recorded. So these are the output waveforms here that explains to us how these diagrams can be related. These waveforms, output waveforms can be related to these diagrams. So we're going to continue from there in the next session. So let us meet tomorrow, or no, let us meet in the next session so that we are able to understand other applications or other types of clippers that we have mentioned earlier. That have got some DC voltages alongside the circuit that limits the conductivity of the sine wave across the input. So these have provisions for adjustments. These have provisions for adjustments to be made to the amplitude of the output signal. Therefore, it uses DC battery to achieve the expected results when connected across the output circuit. So we're going to deal with such examples of biased clippers. So this is a biased series positive clipper, and whatever happens, when we talk of biased, we are having a voltage applied in series with at the output terminal. That's what I described earlier. And also see it, then when this one is biased, it's positive, the diode tries to for bias. And because there's another input here, that means that the input here must be greater than whatever is biasing the voltage so that we get clipping. So during that process, during the positive part of it is that because that was attempted to be forward biased, must move a bit. And this part is limited by the biased voltage. So at the end of the process, we have this. And during the negative half cycle, its conduction is the diode now conducts, and when the diode conducts, then the voltage is added to this point, and that's why you have the voltage fully conducted at this point. So that's what happens with the biased series positive clipper. When we talk of biased shunt, then whatever is causing the clipping must be shunted and must be connected as parallel to the load. And that's why we're talking about biased shunt. So the diode that causes clipping now connected parallel to the load. So this is a shunt. It also gives us the same results from these two analyses. We are going to see that this waveform and this waveform are similar. So basically, that is what it is with the biased series clippers. But also with the biased, this is another biased negative clipper. It also operates on the same principle, that during the negative part of it, this is reverse battery. But because this was biasing the diode, the difference is what appears as the output here, as bias voltage. So the voltage at this point here, if we we do this so that we ask this is also a bias voltage. So the same thing applies, and that's why the broken part means that is a part that has been clipped out. So we're going to have a brief description of this so that we are able to understand in terms of explanation. So clipping takes place during the positive half cycles of the sine wave. Half cycle of the sine wave input. But the output is limited by the bias voltage. This also applies to the negative voltage clippers, to negative voltage clippers. So when you combine this and see both negative and positive, when you talk of combined clippers, so the next thing I'm going to do is to have the combined clippers with the aid of a diagram so that I can be able to explain. We see a scenario where we have combined the two, and what should we expect as the results. So this is a combination clippers, and it's actually constructed from the positive and the negative clippers. So during the positive part of the sine wave, the diode 1D conducts while D2 is reverse bias, and we are able to achieve this. So these levels are still the bias voltage, and the broken part of the output sine wave shows whatever has been clipped out. So during the negative part of cycle, then D1 will be reverse biased and D2 will conduct. So the conduction is such that it cannot actually exceed the bias voltage VB1 or VB2. So that's basically the operation that we need to understand and be able to reflect on this diagram, the way the output appears. So we're going to put that one down. So during the positive part of the sine wave, diode D1 conducts while D2 does not. The output is, however, limited by VB1. So during the negative part of the sine wave, diode D2 conducts while D1 does not. The output waveform amplitude is limited by VB2 voltage. So another thing, how do clipping of the voltage can be varied, clipping of the output, clipping of the output waveform, clipping of the output waveform can be varied by varying VB1 and VB2 independently.